So today we're starting on showing the screen, and we're starting on this idea of a projection operator. And Krista, this was your question last time about how do we generate those pictures. And so I'm glad you just right here. I was trying to stall so that you'd get here. That's perfect. So we're going to use the projection operator to create these symmetry adapted linear combinations of atomic orbitals. So look at that acronym. So that should mean something to you. Symmetry adapted, that's the SA, linear combinations of atomic orbitals. So this is like the 1s on atom A and the 1s on atom B. Are they plus? Are they both plus? Or is one plus the other minus? Those are the shadings that we're going to have. And so we're going to be adding together all of these atomic orbitals that are connected by symmetry. So think about the ethene molecule. The 4 hydrogens could be exchanged in all different kinds of ways. That means those are equivalent by symmetry. And we would use the character table to determine which 2 are shaded and which 2 are unshaded, or if all are the same shading. So that's what we're going to be doing today. But I'm going to show you how the character table is used to generate those. So this projection operator is useful for making these salcs, these symmetry adapted linear combinations of wave functions that have the correct symmetry properties for vibrational wave functions and atomic orbital wave functions that will then be used to make molecular orbitals or vibrational arrow diagrams. And so think about the vibrational arrow diagrams, whether stretching or compressing or bending. We can use the same projection operator to produce those. So let's think about a projector. We have one in every classroom. The projector has a source. It has, and for us, the source will be a particular vibration or a particular atomic orbital. Now look at that source image of the water molecule. Notice that it's an incomplete picture. It's just one orbital that's shaded red, or it's just one bond that's stretching. But both these OH bonds have the same spring constant, the same mass and everything. You can't shake one without shaking the other. But you can conceptually say, okay, what if this OH, if I draw a stretch on this OH, and then I run it through this imaging element called the character table. Every row will produce a different image or no image. And every row is a particular symmetry. So we're going to take this source image here, just the stretch of one bond or the shading of one orbital, and we're going to run that through a particular row of the character table. And then out the other end will come an image that contains the whole molecule. So this is the image that it produces. If we run these two things, this stretch or this 1s orbital through this, we get the full picture of the stretch. And how is that so? Well, take this arrow right here. If we, on the A1 row, if we do an E operation on the molecule, that arrow stays where it is, and it doesn't change direction, okay? So it stays where it is, doesn't change direction. What if we do a C2? Okay, then that would move this arrow over here. And this character underneath the C2 is a +1, so the arrow stays in the same direction. Then we do a sigma XZ. Well, the XZ, this is the coordinate system, X, Z, and Y is here. So X, Y, Z. So the XZ plane, we would reflect that arrow over to the right, and it would be a +1, so it would not change direction. And then we do the YZ, which is the YZ plane, so the arrow stays where it is, and it doesn't change direction. So that's where these two arrows come from. In 2 of these cases, the arrows switched over to the other side. And so we get both of the arrows from the projection operator. Do you follow that? So that we used the A1 row and we got an A1 image. Now, what about the one on the oxygen? We also move that arrow around, but when you add them all up, you have arrows going this way and arrows going this way. The outer parts cancel and the upper part doesn't. And so the oxygen arrow even comes out of this projection image too. So you have all of these multiplications by the characters, you add all of those figures up, and you get the resulting image out the other end. And so that's why it's called the projection operator. We're projecting a particular arrow or a particular 1s orbital through the character table, and the symmetry adapted combinations show up on the right in the image. We could do the same thing with the other rows. We could also do the same thing with a 1s orbital, and we end up with this picture if we go through the A1. So if we have an E, it stays put, same shading. C2, it moves over here, same shading, okay? If we do the XZ reflection, it shoots over to the other hydrogen, same shading. If we do the YZ, it stays put, same shading. Let's see one that that gives us a different shading. So if we take this image and send it through the B2, it stays put, and we'll do this in greater detail in the next few slides. Over here, it moves over to the other side, and the -1 means it's going to be green. Okay. Here it moves over to the other side, and it's going to be green, and then here it stays put and remains red. So I'm going to draw the red ones here like that. So that -1 is whether you change the color or not. And then when you add all those together, you get the B2 row. So we'll see that in detail. I just wanted to show you on this projection image with the little projector and everything. And so these are the salc, the symmetry adapted linear combinations of atomic orbitals, okay? And these are the normal modes of vibration. So they have two different names. When you have the arrow diagrams, that's a normal mode of vibration. And when you have the atomic orbital combinations, that's the salc AOs. And there may be a mathematical reason why this is called a projection operator, but I love the term because it actually fits with the projector, right? You have the imaging element, and you have the projection, and you have the source. So let's do this with the simple molecule like hydrogen. We have this character table, D infinity H. We just have the 1s orbitals, so we can start with this 1s orbital that's yellow colored. We'll run it through this character table, or this row here of the character table. And when we have an E, I'll just draw the little image here. It'll be, see, it's on the top and it stays on the top when we do E. This C infinity, that is all the z-axis of this molecule. It stays on the top, so we're just rotating it 1/infinitieth of a turn around the z-axis, so it stays on that end, and it doesn't change shading. Sigma V's, those are ones that contain the z-axis, and so it stays on top, no change in shading. But on the I, it goes to the other side of the molecule, and it's still a +1, so there's no change in shading. For the S, it's a rotation and a reflection. So it rotates 1/infinitieth of a degree and then reflects down to the other side. So it drops down to the other side. And the +1 character means it doesn't change shading. And then a C2 is a C2 perpendicular to the C infinity. And so it flips down to the other side, no change in shading. So when I add up all of these pictures, I get 3 of the pictures where the ball's on top, unshaded, and 3 pictures on the bottom where it's all unshaded. And so I end up with this picture in the end. This is the image that comes out of that from the A1 row. So do you see how we get that picture through the character table? Okay. Any questions on this before I do the other one? Now there's some monkey business in this character table in these missing columns here. There's some other symmetry elements that go in these columns, and so the A2G and the A1U don't, and the A2U don't exactly cancel out, but they would. So what this is, let's just, so if we do the E, we have it on top, no shading. We have the C infinity on top, no shading. But look at this sigma V. It stays on top, but it's shaded now. And so that shading and that shading cancel each other when you add the pictures together. Here we flip it down to the bottom with the inversion, no shading. Here we flip it down to the bottom. Since it's a +1, we don't change the shading. And here's the C2, we flip it down, and it's a -1. And so it's shaded. And so whenever you have a shaded and a non-shaded, on the same end of the molecule, they cancel each other out. So there is no image here. This produces nothing. It doesn't exactly cancel out because I don't have all the columns shown. But if you were to have all of the columns shown, then this image would produce no result. And so there would be no combination of these 1s orbitals that was A2G symmetry. So even though that's a row in the character table, that doesn't mean that every row in the character table produces an image. The A1 produces an image, so this is A1G. And then let's look at the A1U. So here we have, again, no change to the position of the orbital. Stays unshaded because it's a +1. Stays at the top, +1. Stays at the top, +1. And then now the inversion drops that orbital down to the bottom, and the -1 means it's shaded. The S drops it to the bottom, and the -1 means it's shaded. And the C2 drops it to the bottom, and the -1 means it's shaded. So does everybody see the pattern now? When it's at the top, it's unshaded. When it's at the bottom, it's shaded. You combine all those pictures, and you get this one. And we know the symmetry of this molecular orbital because we use the A1U row to produce it. Yes?
I have a question. So I see for the top one for A2G, I see that the -1 at the top is shaded, but the other one is at the bottom shaded.
Yes.
How do I know when it's at the top or the bottom?
By these elements here.
Okay.
Yeah, and so we operate it. So if it's up here and we do an inversion, then it goes to the bottom.
Okay,
So under inversion, that's why this one is got at the bottom.
oh, okay, I see. So that one.
Yeah, and so we're just taking that single orbital and moving it around depending upon the element,
Okay.
like the operator. So the operator is like an E or a C2 or something like that. So we just move it around according to those symmetry elements. And then the character tells us if it changes shading or not. And if it was an arrow, the character would tell us if the arrow flips direction or not. Yeah. And we could do the same thing. Well, we'll do that in water. I'll show you that in water. So this is how we get the symmetries and the pictures by using this projection operator. We do 3 different molecules today. So we're going to do hydrogen. That's the simplest. There's only 2 1s orbitals. Then we do water. And so we've done this. We've seen this already. This is the MO diagram for hydrogen, and these are the MOs that we have. So let's apply the projection operator to water, and we're just going to, this is just going to give us those linear combinations of the symmetry of the chemically equivalent orbitals. So the hydrogens are symmetry equivalent by symmetry, right? And this will give us the combination of hydrogens that will then mix with the oxygen orbitals. So this is going to be one side of the MO diagram for water. So if we're going to make an MO diagram for water, just a little foreshadowing here. Okay, on one side, we're going to have the hydrogens, and on the other side, we're going to have the oxygen. So, you know, this is going to be the 2p and the 2s orbitals here, and the hydrogens are going to combine in a couple of different ways. We come in with 2 1s orbitals. We're going to have 2 combinations of those. So what are these orbitals? What do they look like? And what are their symmetries? We know this is a 2s, and we know these are 2p's, right? An x, a y, and a z. So we know the atomic orbitals on oxygen. What we're asking ourselves is, how do I bring in the hydrogens into this molecule? They're going to come in as symmetry adapted linear combinations. So there's going to be either the same shading or opposite shading. So we know the answer. Is it going to be the hydrogens with each other or against each other? It's only 2 possibilities when you have 2 things, just like our hydrogen molecule. Well, this is 2 hydrogens in water. They can either blink together or out of phase with each other. So we know those are the 2 combinations. But what are the symmetries in this character table? So this is not D infinity H, this is C2V. And so we can take this molecule and we can start with the 1s on atom A. And so we're just gonna pick this one here, the 1s on atom A. And so we're using this row here, the A1 row. So see, we have the projection with A1 symmetry of the 1s orbital on atom A. So this is sort of the whole thing. P is for projection. The superscript is the symmetry that we've got. The parentheses is the orbital we're acting on. So it's like a function acting on this orbital. And it has 4 elements because this character table has 4 columns. So if we just draw this picture as kind of like we did with the hydrogen, we're doing the projection of A1, and I'm going to draw the picture, right, of just that. You see, that's the water molecule, but we're just operating on one s orbital. See that? And so if we do E on that, it looks like this, right? The orbital hasn't moved. It stays put. And the +1, it means it stays, what it is, unshaded, okay? If we do a C2, it hops over to the other side. Everybody cool with that? And the +1 means it doesn't change shading. The XZ, so this is the XZ plane. See the coordinate system up here? That's the plane that splits the molecule left and right. And so if we do an XZ, it shows up on this side. And the +1 means it stays whatever it is. And then the YZ is the plane of the paper, and so it stays on the left. So we add up all 4 of these. So down here I have this. This is a +1 times the 1s on atom A. Okay, so that's on your left side. And then the next one is a +1, the character here. And it moved over to atom B. So it's +1 times the 1s orbital on atom B. See, the C2 moved it over to atom B. And then the next one is a +1 times the 1s orbital on atom B. That's, again, it's the XZ, so it's reflected over, it's on atom B. And then the last one is a +1 times the 1s orbital on atom A. So all 4 of these +1s add up. So we have 2 times the 1s on atom A and 2 times the 1s on atom B. We can simplify that down to just 1 + 1, right? Instead of 2 + 2, it's 1 + 1. So we just, the coefficient doesn't really matter. It matters if they all add to 0, but we could pull that 2 out front, and we end up having this 1s on atom A plus 1s on atom B. And so the picture that we get from that is this. So we have this picture here, where they're the same shading. And so this is the one where they're blinking together. This is the symmetric combination. Symmetric because they have the same sign. There's a +1 in front of the 1s on atom A and a +1 in front of the 1s on atom B. So they're blinking together. So that's the symmetric combination, but now we know the symmetry is A1. So that this is the A1 combination of the hydrogens. Okay, we've got 4 rows, so let's do the next row. So we can draw, it's the same pictures, and that's one thing that's nice about this, is it's the same pictures, but they have different shading depending upon the characters. So those are the same pictures as before, but the shading is different because of the -1s and the +1s. And so if I look at that, I have those characters in front. I've got the +1 here, so that number is right there. This number here is right there. The -1 is in front of atom B, so this -1 is right here. And then the last -1 here is over here. And you can look down here, you see a +1 on atom A, and then that's canceled by this -1 on atom A. So the coefficient in front of the 1s on atom A is 0. So it's canceled out. And then here's a +1 on atom B and a -1 on atom B. So the coefficient in front of B is 0. So you add all those together and the result is 0. So this row does not produce an end result. There's no image coming out of that row. So there's no linear combination of the hydrogens that has A2 symmetry. It just doesn't exist. Okay. So the next one, again, do the pictures help? They're not in your notes, but I think they help. So here we have this picture. We flip it over, and we have a shaded one because it's a -1. We flip it over, there's a non-shaded one because it's a +1, and then we keep it there, and it's shaded because it's a -1. And you can see the pictures all conflict with each other. And so there's not a B1 combination either. And if you look at the numbers, the characters, we have a +1 on atom A and a -1 on atom A, a +1 on atom B and a -1 on atom B. Everything cancels out. So this tells us there's no B1 combination of these atomic orbitals. So let's finish the last one with the B2 row. Same pictures as before. So now we flip it with the C2 and it's shaded. We flip it with the X Z reflection and it's shaded, and then we keep it where it is, reflection in the plane, and it's not shaded. So do you see the ones on the left are not shaded and the ones on the right are shaded? You add them all together and you end up with the A's being positive, the B's being negative, and so this is the combination that has B2 symmetry. It's 1s on atom A, the opposite shading, that's the minus sign is, of atom B. So that's this picture where that's shaded. So these are the symmetry combinations. This is the B2 combination where, again, they're out of phase. So one hydrogen 1s is expanding while the other is contracting, and then vice versa. So they have a node in the middle, and this is the B2 combination of those two. So now we know the symmetries of those, and we know then which atomic orbitals on the oxygen they're going to mix with, because the symmetries govern what mixes with what. So that's the projection operator applied to the hydrogens in water. And it just, it's what computers are good at, right? It's tedious, but it's not difficult. It's just tedious. Okay. I see a few of y'all writing, so I'll wait. Okay, so we have these 1s atomic orbital combinations in water. This is how you would write them. So the linear combinations of atomic orbitals would be either 1sa plus 1sb or 1sa minus 1sb. Those are pretty simple. I mean, those are the two combinations, either together or opposite of each other, but this is a way to get the symmetries. The nuclei are indistinguishable, so two atomic orbitals will give two molecular orbitals, and then there's three atomic orbitals combining in ammonia, and we'll do that one in a minute. Okay, and so three molecular orbitals result. We have the symmetric combination. So if you have three 1s orbitals, this is always one you can make. If you have 50 hydrogens that are equivalent, then you can have a wave function where all of them have the same sign. So all 50 of the hydrogens are increasing in phase with each other. So you can always write the symmetric combination straight out. But then the asymmetric combinations may not be so easy. So we'll see where these come from in a little bit. We're going to do this one where we get those. But do you see the asymmetric combinations have some plus signs and some minus signs mixed in? And that's a linear combination of those atomic orbitals that we get. So let's combine these salcs with the atomic orbitals in oxygen. So these are the two symmetry adapted linear combinations. We have their symmetries here, so we know what those symmetries are. What are the symmetries of the oxygen atomic orbitals? Well, the s orbitals are going to be A1, so that's straightforward. And then we have the pz orbitals, this z right here. We find z in the character table, and so it's A1. The px orbital, we find x in the character table, so we know that it's B1. And then the py in the character table is B2. We find y B2. So we can find the symmetries of the atomic orbitals very easily. And so we put the atomic orbitals on the right, we put the hydrogen orbitals on the left, they're linear combinations, and then we bring things together in phase and out of phase with no nodes, with more nodes, and so on to make the molecular orbital diagram. So I've got this in your notes. It's all like pretty pictures, I believe, but I've scooched everything over so you can draw them yourself. So maybe on your notes over on the right, we'll draw these ourselves, because these pictures are given by Gaussian are pretty complex, but I'll show you what I would expect if you were drawing this yourself. So we have the A1 combination. So if we were to combine these two hydrogens that are shaded red, we'll just say that red is unshaded and we'll make the green shaded. So this will be unshaded in our little pictures. So let's draw this ourselves. Draw the framework of the molecule like this. And then you can draw 3 unshaded circles. That's good enough for me. Okay, if you were to draw that, I'd be so touched. I'd put it on my fridge. You know, it's like a little kid drawing of a molecular orbital. Okay, so that's beautiful. Okay, and then what about them combining where they're out of phase with each other? They can combine in phase or out of phase. And so what's the out of phase combination? Well, the hydrogens, say they're shaded, and the oxygen's unshaded. So you draw the little framework of the molecule. You draw the hydrogens on there. You draw the oxygen, 2s. And so we're going to shade those. And so we have a node that cuts through the bond. Right? If you got two things combining, then you're going to have sometimes when they're the same shading and sometimes when they're opposite shading. So that's pretty straightforward. Okay. There's also an A1 combination up here where you're connecting with the PZ orbital. It's A1 as well. And so up here, we're going to draw the framework of the molecule. Look at that crazy picture that Gaussian gives us. How on earth are we getting that? Well, think about the PZ. The PZ is this top and bottom part, the red and the green. And so this is going to be the one where the PZ is shaded on the bottom, and that's out of phase with the two hydrogens. So that's the attempt of what Gaussian's showing us. So it's just the PZ orbital that I've drawn is really small in the green area compared to what Gaussian calculated. So Gaussian let this thing expand to minimize the energy of the electrons, and that's what you ended up with. But it's a little difficult to understand. But this came from the PZ orbital that is A1 symmetry. So this has got A1 symmetry. This is A1 symmetry, A1 symmetry. How do I know I'm done with those? I came in with 3 A1s on each side, 2 on the oxygen, 1 on the hydrogen, and now I've got 3 molecular orbitals. Now it seems like I've only used the PZ once. Well, this could also be a little bit of PZ character. And if I had this combined with the PZ where it was unshaded on top, that would just move this node up a little bit. And so in here, in that picture, you have some PZ character, and you have some 2s character, and then you have the hydrogens that are unshaded, or that are shaded. Okay. So there's a little bit of 2s on the oxygen, a little bit of 2pz. That's why you've got these lines both going down to that picture, and that's why this node is very close to the oxygen, because it has that pz character. But could y'all draw those pictures on the right? Yeah, I think you could. Okay. Now let's mix in the B2s. So the B2 orbital, that's the py orbital, and the 1sa minus 1sb. So this is pretty straightforward. We draw the framework of the molecule. We draw the py orbital here, and we'll shade it on the right. And this is the bonding combination, so let's keep the shading on the right for the hydrogen, like that. You see that? It's a py and the 2 hydrogens that match. Well, they could be in phase, or they could be out of phase. Now, the Gaussian's a little hard to see. You can see the hydrogens in there, and there's some node action going on. What's happening? Well, this is what I would expect you to draw. Draw the PZ orbital. You could shade it the same way, but now the hydrogens are opposite. You've got more nodes. Make sense? Yeah. And so these are both going to be B2. And then this next one, I've rotated for the Gaussian picture, I've rotated the molecule sideways so you can see the lobes. But, you know, if you were to just draw this one without rotating, it would be the front of it, say, is shaded and the back is not shaded. Okay. And there's no hydrogen participation in this orbital because this is B1 and there are no hydrogen combinations that are B1. So this is totally non-bonding. So this is B1. If you were to rotate it like I did in the Gaussian picture, you'd have a little wedge here with a hydrogen, little dash in the back, hydrogen, and you'd have the shading on the front and the not shading on the back. Okay, do you see how it's rotated? Okay. So we did it. We drew our molecular orbital diagram of water with all the pictures, so we don't have to depend upon Gaussian to get the pretty pictures. And those are cute little diagrams, so I like that. And so here's, again, we have all of these energy levels. We come in with 6 valence electrons on the oxygen and 2 on the hydrogen, so we have 8. So we start at the bottom and populate those levels from the bottom up. And so this is the highest occupied molecular orbital. And this is the lowest unoccupied molecular orbital. And so we could calculate the transition dipole moment symmetries and so on from the B1 to the B2. So like this is, again, this is the highest occupied molecular orbital here. And so if we were to check out the HOMO to LUMO transition, this would be the symmetry setup. We would have B1 and B2, and in the middle we would have X, Y, or Z polarized light. So X, Y, or Z. We have those right here. The PX has X symmetry, so that would be B1 here. The Y would be B2, and the Z would be A1. And so then we would do the symmetry, you know, with the direct product tables and everything. So we really do need to know the symmetries of these levels, and the projection operator gives us those symmetries. All right. Any questions? Anything that I can clarify? Okay. Let's look at that ammonia molecule and look at those threefold symmetry, because that's kind of a little more difficult. We're going to level up a bit. Okay, so here's the projection operator operating on something with threefold symmetry, and this is the first one we'll have with the doubly degenerate row. So that's kind of interesting. So if we have the projection operator, the different rows and their symmetries, operating on using the characters, and then operating on, say, the 1s orbital on atom A, it's going to move around to B or C depending upon how it's reflected and rotated and so on. Now, most of the character tables, when you look at them, have a column that says 2C3 or 3 sigma V, and it's a really condensed character table. But for the projection operator, you need to expand those out. When it says there's 2 C3s, you can rotate it clockwise 1/3 of a turn or counterclockwise 1/3 of a turn. And so we need to actually expand that column to show those so that the math will work out. And the same with the sigma V's. There's 3 of those. And so one of the sigma V's contains this bond, so that might be a sigma plane. Another sigma V contains that bond, so it exchanges atom B and C, and then the third one would contain the nitrogen hydrogen C bond, which would exchange atoms A and B. And so we'll walk through this and I'll draw the little pictures. So this is what we have for the projection on the A1 row. So this is following this row right here. It's operating on the 1s orbital on atom A. And so if we were to draw our little picture, we would draw a little ball like that. Can you see that? That's my little picture. Kind of like I was drawing my pictures for water. And so we do the E operation. It stays put. Okay. And then so that's I'll draw them down here. So it stays put like this. And we do a C3 operation, and it says that it rotates looking down clockwise over to C. So you see that it's become the ball has moved over to atom C. And it's over here now. Everybody see that? The little stick picture that I'm drawing? And it's +1, so the shading doesn't change. Got it? Then the next one, the counterclockwise rotation moves it over to atom B, so now it's in the front. And it's a +1, so it stays shaded. Stays unshaded. Yeah. Then we have the sigma V prime, sigma V double prime. So these are the reflections. So the first one is this bond here, sigma V. So it stays put and it stays unshaded. So it stays where it is. Then this sigma V prime is the one that contains the B bond, and so it moves over to atom C. So it has moved over to atom C, and the +1 means it stays unshaded. And then the sigma V double prime is this one, and so it moves A over to B. So it's reflecting A over to B. And the +1 means it stays unshaded. So do you see how I have all 6 pictures, and I've got 2 of the balls on atom A that are unshaded, 2 of the balls on atom C that are unshaded, 2 of the balls on atom B that are unshaded. So they're all unshaded. So I end up with this combination here. Again, you could pull that 2 out front and just have the 1SA plus 1SC plus 1SB, and that's what you have, the symmetric combination. So the picture that would be, again, this picture here. Like that. So all 3 in phase with each other. So I only have 2 hands, but they're doing this. They're in phase, expanding together and shrinking together. Okay. Let's do the next row. Look at these +1s and -1s. Well, let me go back to the pictures. You see the pictures? These first 3, look what they did to the balls. They moved the balls to all 3 atoms. Got it? So in just those first 3, we get the ball on every atom, and they're all unshaded if these are all +1s. So these are all 3 +1s. So that means the ball is on all 3 atoms, and the ball is unshaded on all 3 atoms. Look at the next row in the character table. These are all 3 -1s. And so that's going to put the ball on all 3 atoms, and it's going to change the shading. So when I add all of these up, they're going to cancel out. The ball that's on atom A is shaded in one column and unshaded in the other column, so it's wiped out. The one on B, shaded and unshaded, wiped out. So there is no A2 symmetry combination of these. And that's what we see with the +1 on atom A is canceled by the -1 on atom A, and it's the same way all the way across. So let's go to the next one because it's more interesting. Okay, I just don't want to run out of time. Okay, so this is the 3rd row, the E combination. And so we have this picture here where the ball stays put because it's an E, but look at the character in front of it. It's a 2. So it doubles the size of that ball. So we have a really huge 1S, and so then that's the little picture I draw. Then on the first C2, we've moved it over to atom C, so it's over here, and it's shaded. But it's not big, it's just a -1. And then on the counterclockwise rotation, it moves over to atom B, and it's shaded because of the -1. And then all of the reflections, look at those, they have zeros. And so then it's no picture, okay. I'll just say 0, right? Zero. No pictures. So we're left with the 2 times the 1SA minus 1SC minus 1SB. And so that's our combination. So this picture would be something like this. An unshaded ball there, and a shaded ball here, and a shaded ball there. So that's the combination of the E. And this is a doubly degenerate, so there should be another combination. So let's look at some prettier pictures of this. So down here you see that's this one here, 2 times the 1SA. Okay, I think I've got the arrows on this. Yeah, 2 times the 1SA minus 1SC minus 1SB. Does everybody see that in the picture? Yeah. And now, if the node, this is again, how do I know what the other degenerate set is? This is an E, right? So that means there's 2 of them. I only get 1 of the pictures from the projection operator, so I've just got to know how the other picture shows up. I've used the 1SA twice in this one, so I'm going to use it 0 times in this one. It's just the way things mathematically work out. I haven't proven that to you, but and also look at the nodes. The node is this way on the first one, and it's 90 degrees on the second one. And so that's typical for any kind of threefold symmetry. This is what you get. So how would you draw these? Like from the top down, you'd have the nitrogen, you'd have the hydrogen. These are shaded and smaller than that one. And then this would be, unshaded and shaded. Okay, so that's how you would draw those. This one being here and this one being here. You could do that, right? It's just what the circles and their shading. And then on this one, the 1S on atom A is bigger, right? This one's very easy to draw. I mean, it's just all 3 circles are unshaded or all 3 circles are shaded. It doesn't matter because sometime later they're going to change. Any questions on this? This is the way you combine 3 things. You have 2 times 1 minus the other 2, and then 90 degrees, change the node. The one that had 2 is now not used at all, and the other 2 are opposite of each other. So these are both E wave functions. And then we can combine those with the atomic orbitals on nitrogen and actually make the MO diagram for ammonia. We do ammonia or phosphorus trihydride or whatever, the phosphorus analog to ammonia. And we'll do that. I think that's the next lecture. So we'll take these hydrogen atoms and combine them with the nitrogen atomic orbitals and make the MO diagram for this molecule. So these are the symmetries of the symmetry-adapted linear combinations. So here's the basics. If you're given an MO picture, you should be able to assign the Millikan symmetry. If I look at this picture, notice I've got, let's say this is positive and this is negative, just like the x-axis is positive and negative. So this has got X symmetry. This one changes along the y-axis, so this has Y symmetry. So you should definitely be able to recognize the symmetries of these. This one is x squared, y squared is positive in all directions, just like if I squared all my axes. I square the x-axis, the z-axis, the y-axis, it's positive in all directions. And so that one's going to be just like this top row here, A1. So given those molecular orbitals, you should be able to assign the Millikan notation. And as a level up, you should be able to draw these pictures when given these designations. So that would be like the A-level understanding of this. If you're given these descriptions and you say, oh, the 1S on the atom A needs to be twice as big and a different color than the 1S on atom B and the 1S on atom C. So these would be, say, shaded, and this one would be twice as big on the molecule. All right, that's it. That's the projection operator.